Yeah, so in this video we are going to see how eigenvectors, being the ones who capture the main dominant characteristics of the data, that can be the maximum spread of the data, for example, can be represented as the eigenfaces of the image, let's say. So that's what we are going to do in this video. And for the sample space, I've taken 9 images of leaves of different characteristics. Let's see the images of leaves first. Before we begin, let me run them. They are grayscale images with 100 by 100 pixels each. So these are the 9 leaves. We can see that these leaves are having different characteristics. Some may be thin and some may be thick, and some may be curvy, for example. Yeah, some may have more veins, etc. So I have taken 9 different kind of leaves. So this is going to be the sample space, or let's say the data set. Now let's see what are the main characteristics of these images, or let's plot the average leaf of all these to get an overall idea of the characteristics of these leaves. Let's plot an average leaf. We can call it uh, maybe L average, L AVG, L average. L average is going to be just the average of these all. L1 plus L2 plus L3 plus L4 plus L5 plus L6 plus L7 plus L8 plus L9 divided by 9. So this is going to be the average leaf, and let's plot this average leaf also, maybe in a different figure, let's say figure 2, and we'll plot this L average, L AVG. So figure 2, and let's give it the title as the average leaf, and the X and Y are both going to be pixels, right? That's what we have in both directions, pixels. X label, let's call it X pixels, and Y label, let's call it as Y pixels. Let's plot it and see what we get. Yeah, let's see. We can see the characteristics of almost all the leaves. Some may be the shaded region, the darker or denser it is, that shows the common trait of all the leaves, and the lighter region, lightly shaded region, that shows that that trait is more obscure. I mean, there are not many uh, thick leaves, right? So yeah, the thick one is lightly shaded, and but the central area is darker because at least that region is present in every leaf almost. So yeah, we are good to go with our average leaf now. Yeah, we have average leaf. Next, what we can do is, let's make a matrix that will contain all the images. uh, First we'll reshape the image, because we have like square shaped pixel data. Instead, we will make each image as each vector, maybe row vector or column vector, or whatever it can be. So We will reshape the image and each image as a single vector and store it in a single matrix. The single matrix is going to take all the images, each image along each row maybe. So reshaping and assembling the images along the maybe rows, meaning each row is an each image. So this is what we are going to do. Let's name it as A. So A is reshape. First we will take L1. We'll reshape L1 into one row and number of columns. Length of the length of the vector will be equal to total number of pixel, right? That is breadth into height. X pixel into Y pixel. X um, pixel times Y pixel. This should work. And we are going to do that for every other leaf. This for L2, this for L3, this is for L4, this for L5, L6, L7, L8, L9. It's rename this 9, 8, 7, 6, 5, 4, 3, 2, and we have 1. So this is A. This matrix A is going to have all the images now. Are you consistent with our brackets? Yeah, we are. Now we have A. What we do with A is we standardize all the images first. Standardize is basically mean centering and then normalizing. Let's standardize the A. Standardizing the A. Standardizing the A. New A is going to be, let's say, we can write a function actually. For now, let's name it as standardize. Standardize of A. Yeah. Actually, it doesn't know what is standardize of A. Still, it didn't give any error. That's off. So let's write the function. Function. It's going to return standardized matrix. Let's name it as some M, or let's say can be anything. Some good name like std matrix, maybe std mat. We can put it like that. So this is standardize of, let's say, the matrix M. This is the name, the scope of the name M, and the scope of the name M is basically functional. It has scope within the function itself. It doesn't know what is M outside the function. Okay. So standardize M. See, if you want to standardize, we can do it in two ways. One is, or we may have to do it in one of the ways. Like if the images are stored along the rows, like each row represent each image, then we have to standardize along the row. And if we have images stored along the column, like each column is an image, then we have to standardize the column. So for the sake of generality, we'll write the function to standardize along both the directions. Let's say dim, the dimension. So based on the dimension, we'll standardize. And So yeah, let's write this standardized function. What do we do basically? First we have to mean center the data, right? And for that we have to find the mean. So first case, if dim equals 1, if dim equals 1, and this is going to be the case along the column. That is, if each image is along the column, if each column represents an image, let's say like that. If each column represents an image, in this case, let's call it average mu vec. You can call it mu vec is simply the mean of this M matrix along the dimension. Mu vec is basically the mean matrix, right? Mean vector, actually. Mean vector. And then the standardized matrix STD mat is going to be uh, the M matrix actually minus the mu vec, right? Now the matrix is mean centered, or the data matrix is mean centered. Now we normalize this matrix. STD mat equals STD mat dot slash, because this is element wise division, right? So we have to take max from each uh, vector and divide it from the corresponding vector with the corresponding and yeah, divide it for the corresponding vector. This is a max of, yeah, absolute of absolute, because we need only positive values, right? We need only positive values. STD mat, yeah. This actually helps make the data um, attain the scope of -1 to +1. So if it is -10 and minimum is -10 in the data and maximum is, let's say, 3, then if we divide by maximum, then the whole data gets divided by 3 actually, and not the +10. As a consequence, the negative data will be -10 by 3, that is -3 point something, and the positive data will be, positive side will be bound to 1, but the negative side fails to be bound. So we find the absolute of both positive and negative, and whichever is the highest in magnitude, we divide by that number. That's what this essentially represents. Yeah. So this was about the dimension 1. If dim equals 2, that is, uh, if each row represents an image, then again mu vec is same mean of this M comma along the dimension, that is the second dimension, dim equals 2 in this case, and again STD mat equals same M minus mu vec, and then we have STD mat normalized. STD mat equals STD mat dot slash, same again, max of absolute of STD mat, and this is going to be null, and the second dimension is given here. want to specify the dimension, we have to specify it after the null. So this is how we do it in MATLAB. STD mat is now defined for both the dimensions. Let's see. And this should work. Let's try to standardize the matrix. This might be unused, but I have used it. Okay. Let's see. Standardize A, and we will check now by running the code. Keyword end. Oh, oh, looks like we have extra ends here. Let's make the ends. Let's column line 51. Line 51, what's the problem? Not enough input. Yeah, we haven't specified the dimension. The dimension was 2 because each row represents an image. Now run. Again, std mat not assigned the values. So that's function. 51. Std mat also not assigned a value in the execution. Oh. This is SATD mat. That's a typo. Now this should work. Yeah, now it works. Let's check the dimensions of A. Size of A. So 9 rows and 10,000 columns, because uh, each row has 100 cross 100 pixels, and there are 9 images for 9 along 9 rows. So the size of A is 9 rows and 10,000 columns. 9 cross 10,000. That's how it is. So we have A ready made now, and our standardized function is also working well. Now if we go to the next part. So the next part is now we have A, we have the image matrix. Next is finding the covariance matrix. Find the covariance matrix or the correlation matrix or whatever you call it. Finding the covariance matrix. So C is simply A transpose times A. Yeah, simply A transpose times A. Let's now see what should be the dimensions of C. 10,000 cross 10,000, right? 10,000 cross 10,000. Once we have calculated the covariance matrix, we can find the eigenvalues and eigenvectors of the covariance matrix now. Finding the eigenvals and vex of the covariance matrix C. So we take vectors maybe in B and D. Eigenvalues are given as the diagonal components of a diagonal matrix, meaning only diagonal components are going to survive, which are nothing but the eigenvalues, and off diagonal elements are all going to be 0. You can use the function EIG to calculate. Okay, we can write the code, but it's not necessary. However, there are ways. There is something called eigenvalue decomposition for square matrices and singular value decomposition for non-square or rectangular matrices. Currently, that is beyond the scope of our current video. I'll discuss that later because that goes a bit more deep into the mathematics. So let's stick to this now for now. So eigen of C, right? Eigen of C. And how many eigenvalues do we need? Maybe let's take first 8 eigenvalues or something. We can just generalize n evals, let's see, is 8. Uh, we can write here n evals and evals. Yeah. So now we can take eigenvalues and eigenvectors. Mm. Next, once we get the eigenvectors, we have to standardize those two, right? But the thing is, the eigenvectors we get are like each eigenvector is given along each column. Unlike the way we stored the image, like each image was along each row, we have each eigenvector along each column. So the dimension number becomes 1 in this case. So let's standardize this. V is standardize V, but along the dimension 1. So now we will have the standardized eigen vectors. Okay, let's check if this is working so far, because if we go too far and things don't work, that will screw up again. So we'll save, Control A, Control C, because if we lose the code, then that will be a headache again. I have to start the video all over again. What is the problem here? Line 58, NE values is not defined. What's the problem with this? Unrecognized function NE values. The hell? One minute, let me clear the workspace. There's no problem as I see, but there is a problem as I see. C EIGS it is, I believe. Unrecognized function variable NE values. N underscore E values is, there's a problem. Yeah, it's correct. I don't know what was the problem, but yeah, fine. Finally, it works. So there must be. We have asked for only 8 eigenfaces, right? So there must be 8 images, or like 8 eigenvectors, and each should be having uh, 10,000 length. Right? Let's check for that. Size of V 10,000 rows, that is length of each vector, and there are 8 columns, meaning 8 images. That's what I said, because initially we stored the image as a row, but eigenvectors are obtained along column. We can manipulate this if we need, but let's not do that. Let's go ahead, because that will take some more time. Okay, so we have standardized eigenvectors now. Now let's store these in a single matrix, maybe 3-dimensional matrix. But to store it, since we have each image or each eigenface as a column, we have to convert into a square matrix again and store each image. So let's uh, collecting the eigenfaces into a single matrix I. So single matrix I. Okay, single matrix. I. So I is going to be uh, I is going to be whatever the V is. We'll first reshape the V and then store it, right? Reshape reshape V into a square matrix that is X pixels and Y pixels shape. X pixels spelling errors. X pixel comma pixel. Okay. X pixel Y pixel. X pixels comma Y pixel. Yeah. So reshape V and store it in I. Yeah, but we have to store all the images, right? Let's store all the images in the third dimension. Each each iterable in the third dimension represents each image. That's how we can do. For I in no, for loop we write for I equals, right? Was doing some Python kind of stuff. For I equals 1 to n evals. Oh, colon being yeah. So we'll store it in third dimension. Reshape and store it. This should be uh, v of all the rows and ith column, right? Because ith column is the ith image, and ith image is stored in the third dimension of I. What's the problem with this? Appears to change on it. Yeah, this is not very likely the method used in MATLAB because the size of I is changing everywhere. Instead, we can give some initial size to I, and that would be better because MATLAB operates better with matrices, and we are doing it like simple C programming or Python iterable. That is not very likely of MATLAB, but we can do it that way also. So let's keep it conventional. So we have stored all the images in one single three-dimension matrix, that is I. Then let's do this. Let's make a function maybe to calculate the desirable number of calculate the resultant eigenphase as a combination of different eigenphases. Like one eigenphase represents something. If you add the second characteristic also, it will be more detailed. If we add the third eigenvector also, it will be more detailed. So that's how it is. Let's write a function to add more and more eigenphases. To add more and more eigenphases, let's write a function. Maybe let's name it calculate eigenphase. Function that returns maybe the eigenleaf here, eigenleaf, and this is calculate eigenphase of I. You have to give the I matrix and how many eigenvectors or eigenfaces are going to be included, that you should give. Because one will have less details, and more you include, the more and more details will be incorporated. We'll see that later. So, and yeah, so I can leave is nothing but sum of eigenfaces. Eigenleaf plus eigen Oh, sorry. This should be I of I of more and more. We have to write for function, right? For loop here. For 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 I runs from 1 to uh, let's say taking n eigenfaces. Okay, 1 to n eigenfaces. Then I of the first image, like x pixel and y pixel are going to be images, right? X and ith image. We are going to add I eigenfaces. Adds first n dominant eigenfaces. So eigenleaf is like this. Uh, yeah, let's see. Yeah, now it looks better. And if in some case, if the user gives n more than the uh, values that you have already calculated, n evals is the maximum number of eigenvectors you have calculated. So if the user gives more than n evals, let's take n max number of max number is nothing but the number for which you have calculated the eigenvectors n evals. Let's put it like this. So if n greater than n max, let's return an error function, error of uh, number of eigenfaces to plot is more than calculated number of eigenfaces to plot is more than that calculated. Yeah, that you can say. Hmm. This is very typical of Python. Okay, calculated using EVD, eigenvalue decomposition, but that's not the scope of this current project. So and I think we are good to go. Yeah. Okay. So let's now calculate the eigenface. Let's call eigenleaf 1 is calculate eigenface of I that we have to give anyhow. Um, we'll take only one eigenvector for the time being. Uh, 1 and n max is nothing but n evals. So that's the number of max number of eigenvalues or eigenvectors we calculated. So first leaf is ready. Let's calculate the eigenleaf 2 as cal eigenface of I again. Let's take 4 eigenfaces. Let's say again n evals. And nothing but now let's plot it. For plotting, we'll go up and find this command, directly paste it. No wastage of time. And the first is eigenleaf 1 and the second is eigenleaf 2. We'll take it in the new figure 3, let's say. And these, let's say these two are supposed to come in the same figure, right? Let's make it like that. Subplot of it's going to be 2 rows and 1 column. 2 rows, 1 column, first figure. Similarly, for the second plot, it's going to be subplot of two rows, one column, second plot. Um, let's check again. The function is good and greater than max, show the error. Otherwise, calculate the eigenleaf. I think we're good to go. Let's run the code and see how far we have come. Clear all CLC, clear the workspace. Huh. But there is already clear all the browser, so I don't have to type. But anyway, let's run this. Oh, we got an error. Adds first download eigenleaf is not recognized function or variable. So it shows in the function line eigenleaf. Acha, okay. So that basically means we have not defined eigenleaf, right? For the first I equal to 1, it doesn't know what is eigenleaf. Uh, so let's define eigenleaf is, let's say, is a null matrix, zeros of uh, x pixel, x pixel, comma y pixel, pixel or pixels, pixel. Okay, so we'll close the figures first. But this function doesn't know what is x pixel and y pixel again. So we'll write, we'll take it as an input, x pixel, y pixel, and here also we'll give it as an input to the function so that we can create the zero matrix, just an empty matrix, or we can put null, but let's put it 0. Yeah, now it should work, I believe. Yeah, it works. We'll discuss this. I forgot to label them. Let's label this. So title, uh, title, uh, I can leave with let's say using only first one dominant eigen vector or face. Let's say, and there's going to be first how many have we used? I need leave to use as 4. First 4 dominant eigenvectors. And now let's see. Hmm. Yeah, using only first one dominant eigenvector or face. Second is using first 4 dominant eigenvectors or face. So it is clear that using only one dominant eigenvector, we could trace out some important characteristics of an average leaf. But the more eigenvectors we have added has caused us to extract more details. Like, we don't see veins here clearly in the first figure, the upper one, but here even the veins are captured, and the direction and the shapes are better captured in the second, because we have used 4 dominant eigenvectors. Let's try to add 8 dominant eigenvectors, or let's let's keep the first one with one eigenvector only, and let's take the second one to be 8 dominant eigenvectors, all the 8 dominant eigenvectors, and this is going to be 8, just to show. Close the figures, run the program. See, we have captured even better things. what I have captured is even more elaborate here. More and more properties of different leaves the second figure has captured, because it uses first 8 dominant eigenfaces or eigenvectors, while the first one uses only one. So simply this means the more eigenfaces we add, the clearer the data becomes. But yes, we would only need so many of the first eigenfaces to get clear picture, and we can omit the remaining ones. Let's say we can calculate some number of eigenfaces, but we would only need the first few of them. This is in a way called dimensionality reduction. We reduce the number of dimensions. In a different video, I'll actually deal with what is dimensionality reduction and what actually this PCA does. It creates new individual dimensions which are the combinations of existing data. They are nameless dimensions. But yeah, by including more and more eigenvectors, let's put the points here. Let's put the points here. By including more and more eigenvectors or faces, we get more information captured, but we'd we would need only a first few of those to capture almost all the data and can omit the remaining. So this is the essence of this video. So we have taken the sample leaves. So we have taken the sample data set of leaves. Each leaf is having different characteristics. Some are thick, some are thin, some are curvy, etc. And the second leaf is the average leaf, just to see what are the different characteristics in general of these leaves together visualized. And then we have traced out the leaf using the eigenfaces or eigenvectors uh, made of the correlation matrix formed by the actual image values. But yes, in A, you used all the 9 images, but in the eigenvectors, you can use only maybe first 3 or 4. That will give you a good amount of inference about the data. So that is the thing here. We've used 8 dominant eigenfaces, and it could still approximate the average leaf very well. And for that matter, we can use on even the first 4, as we've seen. That also captures well. So this was about this video, and perhaps we end it here now. Goodbye.